what I want to talk about is our efforts to take the universe's baby picture. And this is truly chronological because we'll start with my baby picture. Since so, you know, the hair just came, just a temporary phase, went away again. And I'll actually start back with when I started graduate school, which is kind of interesting to look at how a field has evolved. And start with what I think were some of the questions we wanted to answer in 1982. And I'm going to kind of summarize my talk. I think we've answered these questions. And we can, you know, and as often happens in science, having answered these questions, that defines a new set of questions. And that's what's driving the field. So we now know how old the universe is, what its composition is, what its geometry is, have a basic picture for how galaxies form and evolve. And something that we didn't, I would say did not conceive of in 1982 is that would be in a state where we measure these numbers with precision. When I was an undergraduate and took a cosmology class, people would say to me, I was told that the universe is between 10 and 20 billion years old. And cosmology was not a field where people made precision measurements. What has happened over the last 3 decades is it's undergone kind of an intellectual transition. And I think this is, to me, an interesting field to talk about, both because of what we've learned and because the nature of this kind of phase change. So where are we today? Today, so the glass half full version, is we have a simple model, a model with 5 basic parameters. The age of the universe, the density of atoms, the density of matter, the amplitude of fluctuations that were generated in the first moments of the universe, and how that amplitude varies with scale. So those are basically 5 numbers. We can tell you those 5 numbers. I'll talk about some ways in which we measure them in the talk. With these 5 numbers in the model, we can fit all of our cosmological data. There are a few, I'd say at worst, 2 sigma deviations from the model. But right now, and the data may improve and this may change, everything is consistent with this simple model.
Matter is atoms plus radiation.
Matter, so now, there's the glass half empty. Atoms, as we know, matter includes dark matter.
Atoms is baryonic.
It's baryonic. So this is most of the universe. There's 6 times as much stuff in the form of what we call dark matter. That stuff that we know behaves like ordinary matter under gravity, has weak interactions, or technically super weak, and that weaker than the weak interaction, with electrons, protons, ordinary matter. As far as we can tell, no interaction, or very small interaction with photons. So it's something that doesn't interact with normal stuff much. We have ideas on what it might be. The most popular set of ideas are linked with supersymmetry or the electroweak scale. That's very exciting because we're probing those scales through experiments like the LHC, and through underground experiments that are looking for dark matter, and for experiments that are looking for dark matter annihilation, say from galaxies.
Do we see it any other way than gravity holding things
We see it
together?
only through gravity and its gravitational effects. Now we see it through its gravitational effects not just in galaxies, but even in the early universe. And when I'll talk about what we see in the microwave background, the model only fits the data if we assume that there's 6 times as much stuff in dark matter as in atoms, and that dark matter doesn't interact with ordinary matter. So we have a lot of evidence for it, but we don't know what it is. And people talk about supersymmetric particles, and that's an interesting possibility, but that really, the set of possibilities is much broader than that.
Do we have a clear picture of what dark matter consists of?
No. We have there are interesting ideas. There are ideas we're testing, but it is an open question. And the glass half empty version is atoms are 4% of the universe. That's all we know. About 23% is in dark matter. We know a little bit about dark matter. We know what the rest is in the form of what we call dark energy. Seems to be energy associated with empty space. It could be energy associated with the vacuum, or it could be something else, or it could be the breakdown of general relativity. There's most of the universe is in a form that doesn't cluster gravitationally, that we know very little about, except for the fact that it doesn't interact much with stuff, and that its energy density is nearly constant with time. So the half-empty version is we don't know what makes up 96% of the universe. And we have, on one hand, attractive intellectual framework for generating the fluctuations, an idea called inflation that suggests the universe underwent a very rapid period of expansion during its first moments. But we don't really have a deep connection between that inflationary idea and ideas in particle physics. It's not a fully developed idea. So that's the summary. So now let me begin by first a little special relativity, then a little general relativity, then on to the big bang. Key thing to be thinking about if you're thinking about cosmology is when you look out in space, you look back in time. Nearest, the sun is 8 light minutes away. We see it as it was 8 minutes ago. Nearest stars are a few light years away. We see them as they were a few years ago. Nearest galaxies we see as they were a million years ago. The further out you go in space, the further back you go in time. So then we have to embed this in the Big Bang Theory. One of my colleagues claims that this is actually a documentary. And to talk about the Big Bang Theory, we need to talk about general relativity. General relativity really consists of two ideas. Matter tells space how to curve, and the curvature of space tells matter how to move. Those parts of it are in some ways quite straightforward, and it's simply the understanding the mathematics of how to do those calculations. Relativity. The thing about relativity when applied to the Big Bang that I think is not intuitive for most of us who come to it is the notion of space. In general relativity, space is not absolute. It's relative. You express it in terms of relationships between objects. I like to think about by saying, if I told you that how long it would take to fly from New York to London, London to Tokyo, Tokyo to Honolulu, Honolulu to New York, you'd realize the Earth is round. Right? Just those relative distances. But you don't specify space as an absolute position, but just relative. And what's changing is the relative distances between objects is growing as the universe expands. So the time it would take light to go from here to a distant galaxy is increasing. They're moving further apart. That doesn't mean that they're expanding into empty space. But space itself, if you like, is being created between them. A picture I have when I think about the expanded universe is to think about a very large balloon, and we're ants on the balloon. And that balloon is stretching and expanding, and the distance between the ants are growing. And what the balloon is expanding into is not into space, it's a three-dimensional space, it's expanding into time. And as it's that radial direction of an expanding balloon is the time direction.
When you say balloon, you mean
The surface. The surface of the balloon.
There is no interior.
There is no interior. Or the interior is time.
And the exterior.
And the exterior is the future. So you run it back in time, and you get to a point where the density gets quite large. And you actually get to a point where our understanding of physics breaks down. So I think of the two great ideas of 20th century physics to be quantum mechanics and general relativity. And they both work really well in their own regime. We try to bring them together, and we do not yet have a successful theory of quantum gravity. Our string theory friends are working on this, but without without one that's a dynamical theory of space-time and quantum mechanics that ties together, we can't extrapolate back through the Big Bang. So the thing you should take away is that key thing when we talk about general relativity in the universe is expanding. And I think actually the name of the Big Bang theory, which was invented by Fred Hoyle as a derogatory term, is a bit misleading. I think the right name for the theory is the expanding universe theory. And that represents the part that I think we know and is likely kind of correct and will stand the test of time, is the universe is expanding now. In the past, it was denser and it was also hotter. So the next piece we need to talk about is the microwave background. Space is filled with the leftover heat from the Big Bang. This leftover heat today is at a temperature about 3 degrees above absolute zero, 2.723 degrees. For those of you old enough to remember watching TV before we had cable, when you switched your TV between stations, you'd pick up static. About 2% of that static is the cosmic background radiation. It's just random statistical noise. And to very good approximation, though we'll talk about how we have improved on this and see beyond this, it's basically uniform noise everywhere. And it's everywhere in the universe, this leftover photons, leftover heat. As the universe expands, those photons cool. Because you have an expanding bubble, expanding gas, the gas cools. So these photons cool as the universe expands. We run things back in time, the universe gets hotter. When the universe was half its present size, the distance between galaxies were half of what they are today, the microwave background was not at 3 degrees, but 6 degrees. A tenth is 30 degrees. The further you go back in time, the hotter it gets. So this picture shows the evolution of the universe. Here we are today, looking back in time. As we look back in time, galaxies get smaller because they're assembled out of smaller subunits. The universe gets hotter. And much of this talk will be about looking back 13.7 billion years, back to a time about 400,000 years after the Big Bang, when the universe was hot enough, about 3,000 degrees, that all of the hydrogen in the universe was dissociated into electrons and protons. So back here, there's just a dense gas, plasma of electrons and protons. The microwave photons were tightly coupled to that gas. So when we look out in space, back in time, at microwave frequencies, we're looking back to the universe basically at this moment, when it made the transition from being neutral to ionized gas. And I'll talk about some measurements we've made with some space and ground experiments, the space mission WMAP, the ground experiment called ACT, that look at these fluctuations. So first, let me say something about the Wilkinson Microwave Anisotropy Probe WMAP. This is a NASA mission named after a late colleague, Dave Wilkinson, one of the founding figures in experimental cosmology, who played an important role both in the COBE mission and in the start of the Microwave Anisotropy Probe mission, and passed away from cancer soon after we made our first maps. And NASA generously let us name the mission after him. This mission is what NASA calls an Explorer mission. Every few years, NASA announces they will build an astronomy mission or a space science mission to do something interesting. And tells us, the scientific community, tell us what's interesting. And people send in proposals. When we proposed, there were 45 proposals that went in. They selected 7 for more detailed study. We went off and worked on it for a year, and they selected 2 missions for launch. One to study the early universe, another to study the sun. NASA continues to do this. We were selected in '96, launched in 2001. Their process is continuing. They just selected 5 missions for detailed study a couple months ago. The ones in astronomy are mostly involved with exoplanets, the search for planets like Earth around nearby stars. And putting on my science policy hat, I think this is actually one of the most effective programs that NASA does, because you build relatively inexpensive missions that are focused, sometimes could be high risk. These missions mostly work, but unlike the very big, very costly projects, they're not too big to fail, which means they don't get over-engineered. And you're much better off building twice as many projects that are successful 90% of the time, right, than fewer projects that have a 95% success rate. And when you reach a certain scale, you get too big to fail.
What's the cost of, let's say, WMAP?
In today, it was less then, but in today's dollars, it's about 200 million. So, that's not a trivial amount of money, but, the NASA budget as a whole is about 14 billion. The NASA science budget's about 4 billion. So, spread out over a decade, this is a very small portion of the NASA science budget.
What's one shuttle launch?
It depends how you cost it. If you ask what's the cost of the shuttle program divided by the numbers of shuttles you launch, it's about $1 billion. If you ask what do you save by canceling one shuttle, it's only 55 million. Right? It's all standing Army costs. It's not fuel, it's not anything. It's just you've got this huge army of people you maintain. So in a good year, if you launched 6 or 7 shuttles, that number goes down. A bad year, you launch 3 or 4, or 0, of course, but that number is on a typical year where you launch 4. One of the things that to me is I've chaired too many NASA advisory committees for my sins. It's amazing to me what marching army costs amount to in these projects. So, yes?
Is there a fundamental reason why this expansion should continue forever, or is it possible that it will be reversed in the future?
It depends on the universe's density. So, let me skip ahead 2 slides. General relativity, basically, the density of the universe determines its geometry and its dynamics. The density of the universe is large. Self-gravity makes the geometry of the universe closed. The universe is effectively a closed sphere. The sum of the angles in a triangle are greater than 180 degrees. And the universe will expand, reach a maximum size, and collapse. If the density of the universe is very low, the geometry is negatively curved, expands forever. To go back to where we thought in 1982, we summed up the matter we saw in galaxies, and that implied the density is low, and most likely the universe was negatively curved. When we look at the microwave background fluctuations, one of the reasons they're very interesting is our way of telling us what the geometry of the universe is. we know how big these hot and cold spots should be, because they're the distance a sound wave will travel up to the time at which the hydrogen forms. That's about 380,000 years. So it's about 380,000 light years. So we know how big the spot is. If the geometry of the universe is flat, so Euclidean geometry that we learned in high school is valid on the size of the universe, the size of the hot and cold spots would be a degree. If it was negatively curved, they'd be about a third of a degree. If it was positively curved, it would be larger. So I worked on negatively curved universes in the 90s, early 90s. It was actually Amber Miller's, right here, PhD thesis, where they first saw fluctuations on this scale, saw that this is about their characteristic size. We've now measured that, as I'll show, at a much higher precision, but those are the first measurements. And that's how we know the universe is flat. In fact, that's, to me, one of the most convincing evidences we have for the existence of this vacuum energy, because we can add up the energy we see in matter, and we measure the geometry, and it requires there's more stuff there. The case we're in actually implies an interesting fate for the universe. It implies, as best we know, the universe will expand forever, get ever colder. If this is a universe that will end in fire, in the Big Crunch, it looks like we have a universe that will end in ice, that will get forever colder, forever larger. I think this is a good fate, not that we had a choice in the matter, because it implies a future that extends ever outward. And as Freeman Dyson has pointed out, if we could have thoughts with ever-increasing efficiency, so as the universe gets colder, the energy it takes to have a unit thought decreases faster than the universe expands, intelligent life can persist forever. So we simply need to get more efficient. And the time scales are not terribly daunting. So 10 billion years from now, we have to be twice as efficient at thinking. That should be our goal. That rate of improvement isn't that high. I know most of us are.
You don't decalculate, you should tell.
I don't know. No, I mean I know.
Calculate.
I don't know. I'm actually an optimist too. I actually think the students are getting better. I think the students are coming in better prepared and getting smarter, at Princeton at least.
Is this connected to your cosmology?
No, this is probably connected to my own intellectual decay. You know, I'm probably getting dumber, but you know. So, back to this background radiation. The picture to have of this radiation is really nearly uniform. If you were to observe it, this is the picture. It's the same everywhere on the sky. This oval represents our sky. It's like a globe, but it's the globe around us. So the sphere around us is the same temperature everywhere. If you look very carefully and can make measurements sensitive at the level of 1 part in 1,000, you'll notice slightly more emission coming from our galaxy, and then that the universe is a bit hotter in one direction, colder in the other. This effect is due to the motion of the Earth relative to the large-scale distribution of matter in the universe. This dipole effect or Doppler effect. It was the Kolbe experiment back in the early 90s that was able to make measurements at a level of 1 part in 100,000 that first saw variations in temperature on the large scale. These variations you see in the plane is actually emission from our own galaxy. That's coming from dust and electrons in the Milky Way. What's of cosmological interest are these fluctuations here and here due to large-scale variations in the density of the universe at the level of a part in 100,000 that are producing these temperature fluctuations. So what we want to do with our satellite was make precision measurements of these fluctuations.
So if I may ask, how do you know a priori which parts are really cosmological and which parts are from stuff that happens to be around either the galaxy or the next galaxy?
So there's our galaxy. I'll show you in.
That's easy. We know where it is.
I'll show you in 5 minutes.
Yeah.
The other galaxies kind of showing you that the microwave background's far away and behind other galaxies and clusters. You'll have to wait to the end of the talk, but I will answer that. Well, I will show evidence we have for that. So here's the experiment being launched on a Delta rocket in 2001. And
Were you there?
yes, yes. I was there. It was really exciting. I got to go. I brought my whole family, my brother-in-law, their kids. We all went to Netflix. It was great fun. And we even went to Disney World afterwards.
Did that still seem spectacular? I mean,
Disney World?
yeah, after.
No, I never liked Disney. My wife grew up in Irvine. She grew up with it. She has a romantic feel for it. I grew up in New York. It never meant anything to me, but we took our kids there. But so here's the satellite. You'll notice when you look at the satellite, let's stop this. Yeah, let's. This looks like something you see on a lot of roofs. It looks like a satellite dish. And that's basically what the technology is. You're detecting radio waves, and it's a satellite dish that concentrates the radiation. And the satellite consists of 2 satellite dishes because we want to do a differential measurement, which is a more robust measurement than an absolute one. So we wanted to make a very robust experiment, so we have, it's basically, you can think of it as 2 satellite dishes. After all, it's the stuff your TV picks up. But we just go deep out in space so we get away from the background.
What's the angle difference in the differential?
The angle, there's about 130 degrees apart. And then, so the satellite's out there spinning, so you measure the temperature difference here. A minute later, come back there, and then you wobble. So this is what we actually see. So we measure the sky at 5 different frequencies. Here's the galaxy in the middle. That's emission from dust and electrons. As we go up in frequency, the galactic emission gets lower, 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 lower. And we use the multi-frequency information to distinguish between dust and electrons and microwave background radiation. So you can combine the radiation, the maps in a way to get rid of the, well, first let's zoom in and look at the hot and cold spots, in a way to get rid of the foregrounds. And this represents, for the moment, on large scales, our best picture of the microwave sky. There's actually a better picture, but I don't have it, and people who have it can't show it. There's a European satellite called Planck that's been taking data for about the last couple of years. It's a successor to WMAP. Its results will come out about a year from now. They have a map with about twice the resolution, 10 times the sensitivity, and those results are being analyzed right now. If I was on the Planck team, I couldn't show them to you, but they're coming soon. What I will show you are maps of smaller regions of the sky at higher resolution. And since we know what we're seeing in smaller regions, I'm pretty confident, I think I know what our Planck colleagues are looking at.
If you look 6 months later, is it superimpose them? Are you getting the same picture?
Yes. So we scan the sky every 6 months. So we actually have 9 years of operation, 18 maps.
And they agree.
And they agree. And the difference maps agree with our noise models. And, so I'm a theorist by training. And I spent most of my career thinking about signal. And then I discovered when I became a theorist working with experimentalists, is I spent all my time thinking about noise, right? We spent most of our time not understanding the signal, but understanding the difference maps and making sure that our understanding of the noise and our noise models match the difference maps. And we have many ways of doing difference maps, both the seasons and the multi-frequencies to have various cross-checks. And at a given frequency, we actually have 4 different channels that are highest frequency, so they're independent maps. When you look at the map, one of the favorite features, look carefully, the letters SH appear. Now, this is either a profound non-Gaussian feature with an important message about the universe.
It's just graffiti.
It could be graffiti, and our failure to remove galactic foregrounds in this region means that we're missing the letters I and T. Or it could be, in this I turn to the biologists, I suspect it represents the fact that we have been selected for by evolution to be the people who jump when they see a lion in the grass, even when the lion isn't sometimes there. And we tend to err and see patterns more often than they're there. Those ancestors that didn't jump too often, they're not our ancestors. They were some lion's lunch.
This is that's similar to the philosopher Sidney Morgenbesser's proof that natural selection also explains gravity, because the rocks that shoot up are gone.
Right.
There are other patterns that have been sort of seen that aren't letters
Right.
in these maps. Can you talk about those?
Sure.
Are they significant, or are they still being looked at?
There have been a number of them. I can show you, there's a spot here that's slightly too cold, and I'll show you the distribution, and you can decide whether you think it's a posteriori statistics or not. There is a number of features people have caught.
A ring, right?
A ring, yeah. They're all a posteriori. None of them are terribly significant. I mean, if you define your statistic after seeing it, it's 3 or 4 sigma statistic when you've got 1 million data points. So, as far as we can tell, it looks like Gaussian noise. We've looked at, and it would be great if there was something beyond that, but there's nothing, I think, compelling. The extent to which it looks like Gaussian noise, you can characterize everything by a power spectrum. And that's what's shown here. This is the amplitude of temperature fluctuations, measures a function of angular scale. So basically, you go to this map, you smooth it on a given angular scale, and ask what's the amplitude of fluctuations on that scale. For those of you more familiar with spherical harmonics, you expand the sky in spherical harmonics, and this is the angular power spectrum in spherical harmonics. And I've hidden the letter L with 180 degrees over angle to make this a more popular talk. So the points are our data, the WMAP data in black. These are ground-based experiments in color. This is the data as of a couple years ago. I'll show some more recent data later in the talk. The red curves are modeled. And basically from this shape of this curve, we fit the basic cosmological parameters. The position of this peak tells me the characteristic size of the fluctuations. That gives me the geometry of the universe. The ratio of these peak heights depends on how the sound waves behave. This ratio gives us the density of atoms. This tells us whether the fluctuations persist after the sound waves are gone, which tells me if there's stuff that doesn't couple like sound waves to the photons. That's why these peaks give me a measure of the density of matter. So fitting these curves, we get these basic cosmological parameters and see evidence for the, what we call a nearly scale invariant spectrum of fluctuations. We see roughly the same amplitude of fluctuations in all scales. Yes?
You have a simple model fitting a wide range of data. What do you mean by the simple model? What kind of model?
So the model is a universe described by general relativity, described by physics we know in the lab, assuming the initial fluctuations we call Gaussian random phase. So that,
And this electron.
and then
plasma.
electron plasma, and the odd things about the model is its composition requires dark matter and dark energy. And that has no interaction, so we just specify those densities. And then it's linear theory to compute what happens.
Looks like the error bars get pretty big over in the dark matter bump.
They'll get better.
They get better, all right.
You'll see them get better.
Where is the age here?
The age is coming basically from the geometry. So once you have the geometry and the size of the fluctuations, you get the age. It's easiest actually to see once you assume the geometry is flat. Because then you know the characteristic size of the fluctuations. They're 380,000 light years across. You measure the characteristic angle. You know the distance light's propagated. So given that, you get the distance.
And you don't have to assume anything about the amplitude of fluctuations at time.
No.
The,
No, just
after inflation.
just as long as they're in the linear regime. And it's just their characteristic size.
Is it at all controversial that it's flat? I remember a period when hyperbolic geometers were tripping over each other trying to name which hyperbolic geometry it was.
Yeah, no, I was part of that.
Okay.
I was really interested in the idea that the universe was hyperbolic and compact.
Yeah.
And yeah, no, it's not. I mean,
Well,
I mean, if to be precise, we know that the this radius of curvature is at least 7 times larger than the visible universe size.
Oh, yeah, yeah. Right.
So the radius of curvature is at least about 200 billion light years across. So large compared to the visible universe. The universe could be either positively curved or negatively curved on much larger scales. One of the things that I'm actually very interested in kind of measuring better is just this. There are interesting theoretical models in which the universe is either slightly positive or either slightly negatively curved. And we can measure this much, at least an order of magnitude better than we've measured it now. And it's such a fundamental thing, I think, because we can measure it, we should. But, I stopped teaching hyperbolic or models to the upper level undergraduates because the flat universe is a good enough description to calculate everything. And it's just much easier. It skips a lecture and lets you do something else.
And they did the same thing with Euclidean geometry in high school, too.
Right. Yeah, so to me the most surprising thing is how simple the fluctuations are. That we really, this just is the histogram of the fluctuations smoothed on 4 degrees, 1 degree, and a quarter degree scale. And the red curve is a Gaussian. So it looks really Gaussian. That cold spot is this excess here. So this is significant if you ask, choose this scale and the right filter. You will only see something like this about 0.5% of the time. But you've made a lot of choices. So, yeah.
So when you say there's no evidence for global topology, that just may mean that you can't see far enough that we have what?
Absolutely. Yeah. So, one of the things that I was very interested in was global topology. Could we see that the universe was finite by seeing the same pattern of fluctuations on one part of the sky as the other?
Yes.
And we've looked for that, and we haven't seen it.
But that may
And
be because you're not seeing far enough.
Right. So all we can say we don't have evidence for it.
Yeah.
It just means the universe is very big.
Right.
It could be, we don't know whether it's finite or infinite, we just know it's big. We've looked for non-Gaussian features generated by interactions that generate the fluctuations, and we've not seen evidence for primordial non-Gaussian features. We keep looking, we get more sensitive, we haven't seen them yet. So as far as we can tell, the universe seems to be very simple.
those are the same statement, the Gaussian and the no interactions?
Yeah.
You wrote both of them, but you
Yeah,
the same
one is, yeah, they're really the same. So, you know, you have initial baby pictures, you run them forward in time, 3 randomly selected babies, run forward in time till about half the current age of the oldest child, which is what we, you know, and then you can run them further in time, and, oh, we lost it. And see more recent pictures. If you want children's pictures, I can show. They're also on the computer. You're probably not what you're here for. We do the same thing in cosmology. We take the initial conditions, if you like, that we see, the universe 400,000 years after the Big Bang. We do a computer simulation of how those fluctuations evolve under gravity. This is a purely gravitational simulation. Self-gravity makes structures form. And from these initial small variations in density, large-scale structures emerge, and we see galaxies, clusters of galaxies, superclusters that emerge gravitationally. And we can compare the distribution of galaxies to what we expect. And one of the key things in this is the Sloan Digital Sky Survey, led by my colleague Jim Gunn. Here's the Sloan telescope. And what we can do is map the large-scale distribution of galaxies, measure the galaxy power spectrum as a function of scale. And this is from the analysis of Beth Reed in her thesis, where she looked at the amplitude of fluctuations versus scale. The solid line is a linear theory extrapolation from the model that fits the microwave outlet. So basically, given the initial conditions, we run it forward in time, on what we compare it to what we see, and it matches.
There are no adjustable parameters.
No adjustable parameters.
And that has dark matter, of course,
Right.
huge amounts.
Right.
And,
Well, without
and
dark
that's
matter,
what you were referring to as
without the dark matter, it wouldn't fit at all.
wouldn't be
And,
close.
yeah, and these are the sound waves that produce those bumps and wiggles. We see them in the galaxy distribution. We call them the baryonic acoustic oscillations.
Does this also predict the non-existence of structures beyond the superclustering?
Yeah, so it predicts the spectrum peaks and rolls over. And measurements on larger scales show that. And basically all the pieces fit. You can measure the expansion rate of the universe based on what fits the CMB data. You get an expansion rate of about 70 kilometers per second per megaparsec. That's the Hubble constant, with an uncertainty of about 3%. Our colleagues using the Hubble telescope to measure distance get 72 with an uncertainty of about 3%. You can measure the abundance of elements. We can measure the number of photons per atom from the microwave background by the sound speed. Our colleagues looking at the primordial abundance of deuterium are effectively making the same measurement. Because the amount of deuterium that's produced or left over in the early universe depends on the density of atoms. So one kind of a cosmochemistry measurement, the other pretty much turns out to be the height of the second peak to the first peak in that spectrum. Two different ways of measuring the density of atoms. They agree within their errors, within 5%. We can measure the amplitude of fluctuations by gravitational lensing, looking at the properties of absorption lines, distant quasars, the number of clusters, measurements of the age of the universe. All those pieces fit together. Very dramatically, one of the perhaps most surprising measurement of the past couple decades of cosmology was the observation that the universe's expansion rate was accelerating due to the presence of the dark energy. And some of the most compelling data for that came from measurements of the brightness of supernovae. That as you looked out in space, looked out to higher redshift, supernovae get dimmer. And then in fact, if you go far enough, they start to get brighter again relative to an empty universe model. The points here are the data from the supernova measurements. The line is a curve. The blue is the 1 sigma errors based on the fit to our best fit model. So you don't, you could we could have, if we had done it before the supernova data, predicted the curve from the model. The supernova data actually, this data shown here is actually from after our measurements, but the supernova results were measured first in '97. And this year, our colleagues who did the supernova work won the Nobel Prize at the end of last year for their work showing the universe is accelerating.
But the parameter is just the dark energy.
Just the amount of dark energy.
Which you extracted from the oscillations.
Right.
And you're saying that's the fit.
That's the fit.
With that parameter.
With that number. Right. So today we have a standard cosmological model. Pieces fit. As I said at the beginning, it's a model that's both simple and strange. While the pieces fit, we don't know what makes up most of the universe. We don't know what the dark matter is. We don't know what the dark energy is. So where do we go from here? Well, models make predictions. And this is the amplitude of fluctuations versus scale. Here's the WMAP data shown here, kind of measuring fluctuations to about 1/6 of a degree. The model predicts we should see smaller fluctuations and continue to see these sound waves down to much smaller scales. So one of the things that our group and many of our colleagues have been doing is measuring the fluctuations on smaller scales.
What is the smaller scale that we can do?
So right now, we can measure it actually down to about 1/6 of a 1 arc minute. When we get to scales smaller than about this scale, we start to get dominated by fluctuations generated by galaxies. So we can't see primordial fluctuations in temperature below this scale. When we look at polarization, we should be able to go another factor 2 in scale. That's what we're hoping to start next. We have an experiment where we'll make small-scale polarization measurements that we hope will start in July.
And do you expect dark matter galaxies and dark matter stars or something like that?
Well, where there's lots of dark matter, gas tends to cool and form stars. We think there's actually a spectrum of dark matter halos, from very tiny ones that contain no objects to ones like the size of our galaxy that have lots of stars. Probably around 1 billion solar masses is where you start to always form stars, is our current understanding. And looking at the model today, I'd say the big questions are what's the dark matter, why is the universe accelerating, and perhaps the most profound one is how did the universe begin? What generated these fluctuations that we see?
So the inflation is accepted but not understood, if I understand.
Yeah, I mean, it's the best model we have. It explains the observations. It has a lot of, I'd say, theoretical problems. Let me come back to that at the very end. Well, I'll say just a bit more about kind of the experimental driven progress. That consists of going to smaller scales in the sky. And I've talked about going from COBE to WMAP. Here's simulated Planck data. We'll see this in a year. One of the things that will be very interesting to see is as that data improves, does this model still fit? And we'll know that answer soon. But what we've been doing is going to actually even smaller scales on the ground and zooming in on smaller patches of the sky and seeing what we find. And there are, I'll focus on results from one experiment, one I'm involved with, that's taking place in Chile, in the high Chilean desert, about 17,000 feet, near the border with Argentina and Bolivia, near San Pedro de Atacama. Here's the telescope being assembled. That's actually the ground screen. To see the telescope, you have to go to Google Sky, because that gives you a view looking down. And here's the road, the ground screen, and the telescope. If you've not yet done the exercise of looking at your apartment or house from Google Sky, you can see a lot. And our friends in the NSA have better pictures. So this is actually what the data looks like when you zoom in on a small patch of the sky. And this is nice, it actually shows you some of the blemishes. The atmosphere is pretty bright. The atmosphere is fairly transparent at these wavelengths, but still has an optical depth of 1% or so, and has a temperature of about 300 degrees. So it's a very bright source. And the atmosphere and the detectors produce most of what you see in the raw data is the atmosphere. And you observe it many times, looking at different orientations, cross-linked maps. Where it's not so well cross-linked, you can see the striping. And that's atmospheric in this case. So this is a feature, not the science we're interested in. So we analyze this region here and work hard to cross-link and make accurate maps. And if you look in detail, you start to see some bright spots. That's individual radio source. That's near a galaxy. These interesting features here are actually these shadows are clusters of galaxies. So the microwave background is behind the cluster of galaxies. The light travels through the cluster, hits electrons in the cluster, gets scattered up in energy. So you lose, the cluster effectively casts a shadow against the sky. And one of the very interesting things we're able to do is identify clusters of galaxies throughout the universe this way. And you basically go along, and I'll show you a few later where we filter them out. So you say, there's a cluster, and you point your optical telescope there, and you find new clusters. So we've been finding a few hundred, between the different surveys, over 200 clusters, I think, have been found roughly. So here's how we do that. Take the original map, you filter it, you see sources, you see clusters, go look where there are clusters, where there are shadows, you find clusters. Some of the sources are indeed nearby galaxies. So here are, you look at the map, you actually see a slightly extended source here. This is at 148 gigahertz. Higher frequency, 220. Resolution's a little better. You can actually clearly see it's a resolved disk. You look at optical light, and you're seeing emission from the dust in a nearby galaxy. And we see a bunch of nearby galaxies. More annoyingly, we have lots of distant galaxies that we can't really resolve, that are limiting foreground on small scales. This is the biggest cluster we found. We named it El Gordo. This is casting a shadow in the microwave. This is the cluster in the optical. It's a very interesting system in the optical. You can see there's actually one region of excess of galaxies here, another up there. There's two big objects merging. In the X-ray, we can see a very bright hot spot centered on one, the shock from the merger. This is an interesting system cosmologically to see something this massive. It's actually probably, now the most massive object in the visible universe that we found so far. That's bound. But it's a very interesting laboratory to understand how galaxies are assembled and clusters are assembled. So I think this becomes interesting astrophysics. And here's another picture of it. And you can actually see quite nicely. Let's see, here's a gravitationally lensed arc. So you can actually see the effects of the matter in the cluster serving as a lens, distorting images behind it.
How distant is that?
The distance to this, it's about a redshift of 0.87. So the distance is, it's about, I think it's 5 billion years ago, 6 billion years ago. The scale across the cluster is about 3 million light years, about a megaparsec. And it's an infrared image. It's a very hot cluster, very massive. Okay. As an early universe cosmologist, all these are foregrounds. We mask them, we get rid of them, we do the best we can to remove the dust. We want to study what's there on small scales. We want to ask, how does the model do on smaller scales? So I'll show you data both from our experiment, from an experiment in the South Pole, led by our colleague John Karlstrom at the University of Chicago. One of the things to note is we're seeing the same thing. Here's our raw maps. The South Pole telescope has the advantage of being a bit colder site, which gives it some advantage. It's a site where they can't cross-link, so they can't measure the large-scale fluctuations as well. So to compare our maps, we have to filter out the large-scale fluctuations. Here's a filtered version of our map. Here's their map looking at the same region. A nice way to compare them, so if I can pull this up, their map, here's our map, same region of the sky. This is a strip about 5 degrees wide, 20 degrees long. And these are two independent experiments measuring fluctuations at the level of a couple microkelvin, and we're seeing the same thing. In fact, if you look carefully, there's some variation in some of the sources, because we're seeing them at slightly different times. Radio sources vary. They do separately. Compute the angular power spectrum for the two experiments. Our points are shown in blue, theirs are shown in red, and way out here, if you look carefully, we start to get contribution from dusty galaxies that are pulling the spectrum up a bit. But you can see not only do we see the first peak seen, those 3 peaks we saw in WMAP, but we see peak 4, 5, 6, 7, 8, maybe 9. The model fits the data very well. Planck will measure fluctuations in these scales across the whole sky. The Planck errors will be about 1/4 of the errors you see on this plot. So the Planck data either will show a very nice fit to the line with smaller error bars, or will show a deviation, and with the smaller error bars, the deviation may be significant in an interesting way from the current best fit model.
SPT looks biased slightly high, but
it depends on their source. So the SPT data is a little bit higher than the
just the highest L's.
It's just the highest L's.
And sense what?
It's, I think, different point source cuts.
Oh.
So the source counts. Okay. Yep. Okay, let me show 2 more plots and then I'll stop. One was this question of how do we know what's behind us? And one of the ways we can actually see the deflection that occurs in the fluctuations as they travel along line of sight.
So I don't understand what you're explaining here.
Oh, in this plot, why these points are a little bit high, the red points. And what I've not included is the contribution from sources, which the data actually extends out here and gets completely source dominated. We've actually, this is work we should show. One's current thesis student is doing work on gravitational lensing of the microwave sky, how it's been deflected, measuring the amplitude of lensing signal as a function of scale. The red curve is our theoretical prediction. The points are the data, and we've now detected, in this plot, I think it's about 3.8 sigma. I have stuff that was emailed to me last night now at 5 sigma, as that we get more data, showing that we see lensing, we see the deflection at the level we expect. Things are moving quickly. A year from now, we'll have data from Planck. So I've mentioned already, we have a polarization experiment that's much more sensitive, that's going to go to the sky in July. Our colleagues in the South Pole are also doing polarization measurements, and we'll see. So let me conclude. Hope you got a sense that cosmology has really been in a golden age, that we now understand many things that we didn't understand in the past. It's often true. We've answered some questions, raised what I think are deeper questions. The existence of dark matter, the existence of dark energy, the notion that the universe underwent this period of rapid expansion called inflation, all implies that there's a lot of new physics that's there, really new fundamental physics that we need to understand. to understand the universe. These are questions that we hope to address both observationally, experimentally, and theoretically. I've been emphasizing kind of the observational side of how we improve the data to address this. The other part of the story is, theoretical advances, new ideas that help us to address these questions. I think these are questions at some level. I think these are questions that are questions actually of fundamental physics. Understanding dark matter and dark energy are things that will require novel ideas from particle physics. One of my hopes for the coming year or two is, in addition to seeing the advances in these cosmological experiments, that we'll see things coming out of the LHC that will lead to new ideas that will help us address some of these questions. But it's clear that, to me at least, that the coming years I think will be as exciting as the past few years have been, and that we'll continue to see exciting advances in this field. So let me stop there.
Well, thank you. So more questions?
Well, I would like to ask, if people find the Higgs boson where they expect it to be, what effect would that have on your picture? Does that actually make any difference?
Would you repeat
the question? Is what does the Higgs tell us?
Right. If you find it where people, if it's found where people expect it to be.
Well, if the Higgs, so I'm not a particle physicist, and people, in the audience, correct me, but where the Higgs seems to be is actually in an interesting place, because it requires that that there's got to be more than just the simple Higgs. And maybe there are two Higgs. Maybe we'll see evidence for supersymmetry. If we see evidence for supersymmetry, that may point us to what the dark matter is. This simple model would be more convincing if at least we weren't inventing two things but just one thing, and we knew what the dark matter was. And there's, I think, hope that the LHC will at least not see the dark matter directly, which is possible, at least see the physics associated with the new physics that generates dark matter, and will understand or start to understand some of that sector better. So I think that's one of the hopes in the LHC. We could find something more profound. And to give my favorite Kabbalistic explanation of dark energy. We know two scales in physics that are I think are important scales. One scale is the electroweak scale, the scale at which electromagnetism and the weak forces are unified, and this is the scale the LHC is probing. The other scale is the Planck scale. That's the scale in which quantum mechanics and gravity come together. If I create a new scale, and say, maybe there's new physics at this scale, and say the vacuum energy should be this scale, I get the right answer. Now,
for what dark energy is?
For what dark energy is. Now, do I have a theory that does this? No. But I'm reminded of a story I was told in college of the Putnam exam, which the mathematicians here know. It was a very difficult exam. And a student who knew how a proof went, but didn't quite remember it. He knew how it began, he knew what it ended. So he wrote the beginning of the proof and wrote pages 1 and 2. Wrote the end of the proof and wrote pages 9 and 10. Put a paper clip on, handed it in, and supposedly got a complete perfect score for that question because they assumed they'd lost the missing pages. So I can write a paper on the cusp explaining vacuum energy in that form.
What is that energy?
This energy scale here is the vacuum energy that we observe. Turns out that unit is mass to the fourth, where that's this scale here. Now, why is this scale?
What is that scale?
The electroweak scale.
No, he's asking numerically.
Oh, numerically it's about 10 to the minus 40 eV.
Sort of in the neutrino mass.
So neutrino mass range.
You know,
Another
something-
possibility is that neutrinos acquiring mass. We're just we're just undergoing a phase transition. It's a temporary phase that the universe is accelerating, and we'll stop accelerating. You know, we don't know why the acceleration is happening now.
Something that maybe should be added on the dark matter, just to sort of complete the picture, is there are all sorts of other studies that people are making in case it does have non-gravitational interactions with it. So he just was mentioning that maybe it gets produced at the LHC, we can hope. But people are also doing experiments where they have very big detectors deep underground in the hope that dark matter just zooming through the, because we're going through a sea of dark matter if it's particulate size. And so maybe if it interacts with matter, we could detect it interacting. Of course, you have to do it deep underground to get cosmic rays out of the way. And then the last way people are looking is looking for annihilation of dark matter, perhaps in the center of our galaxies. Or they can, dark matter could also be very big. It could be small black holes or something like that, which David has worked on.
Yeah, I mean, and we're also looking to see if it has other astronomically observational gravitational effects.
Yeah.
So if the dark matter is a small particle, light particle, it might not cluster on small scales. So there's a lot of interest in studying the smallest galaxies, dwarf galaxies, because if you look at the theoretical predictions on small scales and what we see in dwarfs, things don't fit terribly well. On small scales, gas physics matters a lot. So we don't know whether the deviation is telling us something about the physics of star formation or about the dark matter. But people are pushing hard on it.
Well, and also I guess we shouldn't forget to mention, maybe it's not in our universe at all, but there's another universe that's on a brane a millimeter away or something, and it's stuff over there, which of course we won't ever detect because it doesn't ever get into our experiment.
No,
but it can pull on us.
It can pull on us, right? That's something that has very weak coupling with us, or no coupling. So, you know, we can be,
it's amazing the different
we can be lucky, and it could be something that's within our grasp soon. The kind of heartening part is for a wide class of models, the LHC is getting into a regime in which we might see new interesting physics associated with dark matter. But those models may not be right. So I have some hope that a decade from now we will know what the dark matter is. I think that's not unreasonable. I have very limited hope that we'll know what the dark energy is. There really isn't anything obvious on the horizon that would lead to some insight on what the dark energy is. You know, the other, I think, big open question is, what produced these fluctuations? Did the universe go through this period of accelerated expansion we call inflation? So we think during the first moments of the Big Bang, soon after it, the universe was dominated by energy associated with empty space, vacuum energy, and underwent a period of acceleration. When this idea was proposed in the 80s, it seemed very speculative. An idea that came out of people thinking about phase transitions, gravified scales of particle physics, and it made a number of interesting predictions. The geometry of the universe should be close to flat. This is at a time which the data said be hyperbolic. That turned out to be right. Predicted that the fluctuations should be Gaussian, nearly scale invariant. We saw. Predicted the fluctuations are what we call adiabatic, the ratio of electrons to photons, electrons to dark matter over there. There's the same as over here. There's the simplest one. Gaussian fluctuations. All those things have held up. One of the most distinctive predictions of the model is there should be very long wavelength gravitational waves. And those gravitational waves actually predict a pattern of polarization that we should see in the microwave spectrum. We haven't seen it yet, but the experiments are only now reaching the level of sensitivity that we might hope to see them. So again, one of the potential breakthroughs on the experimental side over the next decade is the experiments will get sensitive enough that we see these pattern of polarization produced by gravitational waves. If we were to see that, that would be very direct evidence that we saw that something like this inflationary outlook happened. If we see it, it'll also rule out some of the alternative models. One of the most interesting alternative models is that before the universe today we see the universe expanding. Perhaps before the Big Bang, the universe underwent a period of collapse. So you had a collapse, a crunch, somehow. And I like this, there's a cartoon where you have this calculation and there's a missing piece and it says, and a miracle happens. And this sort of has this form, apologies to my colleagues who work on this, that you had the universe go through a big crunch, emerge with the right properties to go back into the Big Bang expanding phase. In those models, the fluctuations are generated in the collapse phase. And those fluctuations would not include gravitational waves. So if we were to see them, we'd rule out that class of theories. So, on one hand, thinking about what was there before the Big Bang seems highly speculative. Yet there are people who are doing experiments that may rule out those models. So we'll see.
All right, so on that note, let's thank David again.